Fine. Well, I'm going to talk about supernova-like transients that are powered by extraordinary mechanisms rather than ones that people usually associate with supernova. To begin with, to just give you a sort of a feeling how diverse the range of these kinds of luminous transients is. I've listed a few of those. Is definitely not exhaustive, and in both places I've marked those that I'm going to talk about a little bit more. And with the bracket, I marked those where this engine power, which I'm going to define in a moment, for which it is relevant, or at least in some events it will be relevant. Okay, but usually these kinds of explosive transients, supernova-like, but not necessarily supernovae, they are associated with what calls compact objects. Either black holes, neutron stars, and sometimes also white dwarfs are associated or are sort of put in this nomenclature. And here just I sort of listed the events that are associated with one type of these compact objects or another. For example, supernovae, they can be related to both neutron stars and black holes. Gamma ray bursts, GRBs, the same way. So when we talk about gamma ray bursts, we can talk about two different kinds of explosive events. One type is associated with the death of massive stars under some special circumstances, when it launches a sort of a relativistic and highly energetic jet that drills its way through the entire star, and when it's pointed towards us, we see an intense burst of gamma rays. There's also another type that's associated with emerging compact objects, which are the same types of objects, at least in some cases, which give us the gravitational wave signal. Also, I'm going to be mostly talking about these so-called superluminous supernovae, which are supernova-like explosions, but for some reason they are about 1 to 2 orders of magnitude more energetic than ordinary ones, and there are sort of other differences, on the more fundamental differences from ordinary supernova. There are also so-called kilonovae, which are sort of in between ordinary novae and supernovae, which are associated with certain types of these compact mergers, gravitational wave events. When these merging objects are neutron stars, then they will sort of throw out part of this debris that they make during this merger, and this debris can power optical emission, in which case this thing is called kilonova. Okay, I will not stay here for too long. I'll next try to sketch a general picture what happens if this kind of explosive event takes place. Well, you have some kind of energy source. You have a stellar envelope that is blown apart by this initial explosion that takes place in this supernova-like event, and you have possibly several kinds of energy sources that will subsequently power whatever emission we see at the end of the day. So with classical supernovae, the two most prominent or widely discussed mechanisms are radioactive decay of 56 nickel that is synthesized during the core collapse. Also, the shock that blows the envelope apart heats it up, and you can see residual heat in some cases from this envelope as it becomes more and more transparent. This is sort of the classical core collapse supernova energy level powering mechanisms. But what I'm mostly going to be talking about is the so-called central engine idea. When you make this supernova, you usually also make a compact object in the center. Usually it's either, well, almost always, I guess, it's either a neutron star or a black hole. And when it's born, especially in the case of a neutron star, it's born with a high magnetic field and high spin. So you have a lot of rotational energy of this object, and you have a strong magnetic field, which sort of provides a mechanism of tapping into this energy. Basically, you have a dipole, intense dipole radiation that can power the event from the inside and heat the envelope up. Also, you can have so-called fallback accretion. When the star blows apart, not all of it becomes unbound. You can have some material that actually remains bound to the central compact object and can be accreted after the explosion over some time scale onto this compact object, and also release a lot of energy. So these are the sort of so-called central engine models. Also, when the ejecta is blown apart and there is something around, for example, some stuff that has been thrown out by the star during its final stages of evolution, then you can have this ejecta running into this material, creating shocks, and also powering luminous emission. Okay, so I don't want you to go through all this formulae. I just here wanted to give you just a rough idea of the energy scales that we are talking about in these different mechanisms, starting with radioactive decay, and all this is engine models, also shocks. So you can see that actually these mechanisms, particularly these so-called engine-powered mechanisms, they have quite a bit of energy, and then often times quite a bit more than would be available from radioactive decay. Of course, it always depends on this parameter, how much mass you blow out, how much nickel you synthesize, and so on and so on. But just to give you a very rough idea. Now, you have some mechanism now that deposits the energy, be it radioactive decay or some kind of a central engine. Now the next question is what happens with this energy? How does it convert to the emission that we hope to see at the end of the day? So basically, what if the source is internal to the expanding envelope? Well, the envelope initially is thick. It has to radiation initially is trapped, and we can only hope to see a luminous transient when this envelope has expanded enough so that photons can diffuse out. And very roughly speaking, this peak time is expected when this photon diffusion time through the ejecta becomes comparable to the expansion time. Why is this? It's basically because the expansion time scale also gives you the adiabatic cooling time scale. So if the expansion time scale is short and the diffusion time scale is long, then the radiation basically is trapped within this expanding ejecta, and it will lose most of its energy before it has a chance to get out. So you expect the supernova or supernova-like explosive light curve to peak when these timescales become more or less comparable. So and this peak timescale, well, it's shown here. Basically, this peak where I scaled the quantities like the envelope mass and its velocity to typical values one expects in this superluminous supernovae that I'm going to talk about in a moment. Also, one can roughly say what is going to be the peak luminosity, which basically is governed by the so-called Garnett's law, which means that whatever is powering this emission, the peak luminosity is approximately equal to this luminosity of the power source at this peak time, which is sort of intuitive. Okay, so let's be a little bit more concrete, talk about these so-called superluminous events that I've mostly worked on. But to start, I guess everybody here knows what's written on this slide. Basically, About ordinary supernovae, basically what you have is, if you have a massive star at the center, it will, when it runs out of hydrogen, it will burn progressively heavier elements until it gets to iron, which it cannot burn anymore. When this iron core becomes large enough, it cannot support itself and collapses until it reaches nuclear densities, whereupon the equation of state suddenly stiffens, and there is sort of a bounce back, which can launch a shock throughout the entire stellar envelope and in principle unbind it. Well, in reality, it's much more complicated than that, because, well, it's a long-standing problem in simulations that this mechanism alone is not actually, in most cases, sufficient to unbind the star. You need something else. You need, well, and it's get very complicated there. But basically, you need a strong neutrino heating to revive the shock, so that it doesn't stop with some radius within the star and actually goes for the entire star and goes to pi. And if you are successful, at the end of the day, you will have a compact object in the center and the envelope that gets blown apart. And all this explosion itself takes place over a time scale of seconds. Okay, so superluminous supernovae. They were discovered about, well, almost 20 years ago now, with robotic surveys, and it turns out that there is a class of supernovae that are about 1-2 orders of magnitude more luminous and more energetic than ordinary ones. They are also extremely rare, about at least 3 orders of magnitude rarer than normal core collapse supernovae. And the first question you might ask about these, well, given that they are so luminous and so rare, is that maybe they are just sort of tail ends of the normal core collapse supernova distribution. But it turns out that there is something else going on. And you'll get a hint when you start looking at the plausible energy sources for this kind of events. Well, the first idea, like in normal core collapse supernovae, what about radioactivity? Well, the superluminous events, if they are 100 times more luminous or more energetic, they would require 100 times more radioactive nickel to power this emission. And this, in principle, is plausible if you have a so-called pair instability explosion of extremely massive stars, probably about three stars. But there is still a problem that if you have so much nickel, your overall mass has to be very large as well. So, you cannot have a sort of a nickel fraction to the total higher than some value. It becomes unphysical. So if you have a lot of mass, then you, from this T peak timescale that I showed, you will find that the timescale becomes extremely long that you would expect in this massive envelope. And this is not what is observed. You see them peak over a timescale of weeks, maybe months, but in this case you would expect like 100 days or so. So there is an inconsistency there. Yeah, and it's a good time to. The problems don't end there. In some cases, which are not so many actually, up to this point, you can observe them since they're far away. It's quite rare, but you can observe them out to a very late time. But if you do, you can see that it's again the late time light curve is not consistent with radioactive decay. When you look at on the top panel, the red points on the face of it, it looks like it goes the same way. If you connect this late point and the early ones, it would be consistent with cobalt decay, which is about the nucleus of nickel 56. But the problem is that the ejecta has already expanded enough by that time that the gamma rays that you get from the cobalt decay, initially the energy is in gamma rays, they are not sufficiently well trapped and reprocessed into the optical.
So you would expect that the actual light curve that you see not track the decay rate of the cobalt to be steeper. In the best case that we have for this late time observations, this SLSM 2015 PM, which you could observe for a couple of years, you can see, you can more clearly see this discrepancy. The late decay is much shallower than you would expect from radioactive decay. So it doesn't work. Okay, a few words about the nomenclature before I go further. Basically, a similar way than you do with ordinary supernovae, you can divide them into two classes, or two types. The second type is one which does exhibit hydrogen lines, and we think that actually in this case it's not powered by this so-called central engine, and actually you can explain them in terms of shock interaction with the ejecta with something that is lying around. What I'm going to concentrate is type 1 events, which show no hydrogen lines, but they show broad lines of oxygen and other elements like silicon, and so on. And these broad lines indicate explosion speeds of the order of 10,000 kilometers per second. Their hosts are generally dwarf galaxies with high star formation rate and a metal core. And there is an overlap with long gamma ray burst hosts. And this is one hint among others that the progenitors of these two kinds of events could be actually similar. One can also show quite convincingly that the power source in the case of this type 1 events is probably internal to the ejecta, as opposed to this like external shock interaction with the ambient medium. There are several lines of evidence for that. So if you have an internal power source, which is not radioactivity, what else is there? It is probably some kind of central engine that continues to pump energy into the ejecta after the initial explosion. Okay, so there are several, or at least a couple of options for this central engine. In simple terms, the energy deposition rate or the engine luminosity can be roughly written using this kind of formula. Basically, what the shape would be that it's constant for some. Well, this is what the rate occurs. It's constant for a certain amount of time, and then decays according to some power law. This power law is different depending on the specific model that you're talking about. It's like late time goes like t to the -2. We're talking about the magnetar, which is this fast spinning, highly magnetized neutron star that's born in the explosion, and you get slightly different values for this late time decay rate in different models, whatever's your favorite. So our favorite is the magnetar model. One appeal of this is that it's relatively simple. You have just a neutron star. It has its moment of inertia, which slightly depends on the equation of state, but not by a huge amount. It spins, so you have spin period, and this gives you the available energy, rotational energy. Also, it has a strong magnetic field, or if it has a strong magnetic field, it will spin down over some time scale that you can also work out pretty easily. This is of the order for this normalization is of the order of a day. So it's a time scale over which it deposits its rotational energy into whatever is around. And well, when you do the modeling using this model for the superluminous supernovae that we have observed so far, then you get typical values of the birth periods of the spinning neutron star, which is a couple of milliseconds, and the magnetic field at birth, which is of the order of 10 to the 14 Gauss. And we know that actually, that these kinds of fields are plausible because there are galactic magnetars which have been shown to have actually magnetic fields even higher than that. Okay, so what's going on then? You have the ejector that's being blown apart. You have the center of magnetar that inputs this so-called striped wind. Essentially, it's basically pointing flux, electromagnetic energy with very little, but not non-zero amount of particles in it, mostly electron-positron pairs. And what it does, if it has enough power, it will inflate a cavity within this medium that is well stellar envelope essentially, and at the interface it will create a strong shock and convert this electromagnetic energy into it deposit into whatever particles are around. But the issue is that you have relatively few. It's relatively evacuated, relatively few particles. So the energy per particle that you deposit there is quite huge, and it's characteristic of when it's translated to photon energies, which is what the electron-positron pairs will emit. The characteristic energies are in gamma rays. So the question becomes, what happens to those gamma rays? We have all the energy in gamma rays, but actually we see these events mostly in optical. So, but the issue is that the gamma rays are initially trapped in this ejector. They cannot get out because it's still early, and they will basically bounce around in this ejector, and at each step they can be absorbed, re-emitted at low energies, and so on and so on. Eventually, they can be reprocessed into optical emission, and this is one question that we try to compute with our simulations from first principles. How does this process take place? What are the microphysical processes and so on? Okay, so we did numerical modeling. Basically, it's a Monte Carlo code that we developed, which follows basically all the particles and all the photons as they bounce around. The electrons emit new photons, photons run around, get absorbed, you create new particles, these new particles can emit new photons, and so on and so on. Basically, we followed all these processes, and at the end of the day, the photons can get out of the outer edge of the envelope, at which point we collect them and find out what the luminosity is, what the spectrum is, and so on. So I'm not going to go through all those processes. Just to highlight that there are many that are relevant in doing this. Okay, I will skip this. Okay, so again, this is slightly repetition, but well, you have the peak luminosity when the diffusion time becomes comparable to the expansion time. At that time, this is something that we checked, and we found out that at the peak time, typically you have almost complete reprocessing of these initial gamma rays that come from this region to optical that gets out of the ejector. Basically, whatever you inject, whatever spectrum in gamma rays, it comes out in the optical domain or in the near optical domains. Now this you can also ask about the efficiency of this mechanism. You have the engine, which deposits its energy over some characteristic time scale, which is the spin down time scale that I showed earlier. And you have this peak time scale where this optical photons can get out. So you find that actually the whole setup is most efficient when this peak time scale is comparable to this time scale over which the engine deposits its energy. Okay, so what happens after the optical peak? Well, the ejector continues to expand. The engine power at late times goes like, well, in the magnetar case, like t to the -2, but this is, well, typically not what is observed. So what's going on? Well, as the ejector expands, there comes a time where these gamma rays that you have initially, they start leaking out before they have time to be thermalized or reprocessed into the optical. You can define sort of initially it was like the phenomenological quantity, like this thermalization optical depth, basically a quantity that characterizes the efficiency at which these gamma rays are processed into the optical. You can also define a thermalization opacity correspondingly. And if you take it to be constant, which was done ad hoc, basically by previous simplified models, then you will find that at the late time optical luminosity goes as about t to the -4. So whatever is between this t to the -2 and t to the -4 is the energy that leaks out actually somewhere else, mostly gamma rays. But this was done with, well, it agrees with observations, but it was done sort of ad hoc without physical justification. And this was also one of our main goals, to provide physical justification, or well, to check what this effective thermalization capacity is from first principles, rather than assume something. Okay, so as I was saying, when the ejector dilutes, you have this gamma ray leakage, which gives you this incomplete thermalization. Some gamma rays just escape before they have time to reprocess. And this depends on the optical depth, which I show here for this 2015 BN as a function of photon energy at different times. So you find that over the first several months, well, wherever you are here, the opacity is much larger than unity, so you have completely efficient thermalization, no gamma rays can get out. At about 1 year, you start to open a window here, this domain, which is mostly the Fermi-Lab domain. You expect these high energy gamma rays to start leaking out first in this window. And as time goes on, this window broadens and broadens, and eventually, over time scale over a few years, you can also expect TV emission, which in principle could be detectable by ground-based scientific instruments. Okay, some results of our simulations. Well, here are spectra at different days, again, for this 2015 BN. As promised, initially, well, this is the high-energy spectrum, not the optical one. As promised, the transparency window initially opens in the multi-MeV GeV domain, this black line, where you see emission, well, we predict emission first, then it quickly rises up, and by the time it reaches its maximum volumetrically, you have more or less a flattish spectrum that in UFnu, meaning that you have approximately equal amount of radiation energy per logarithmic photon frequency or energy interval. As time goes on, this spectrum becomes harder, and its peak shifts to higher and higher energies, photon energies. This is simply because this transparency window broadens, and you can get higher and higher frequency photons out. Now, here's one phenomenological parameter that we have, which is very hard to constrain from first principles, is this magnetization after the shock, after this energization event within this nebula. but it turns out to be, unfortunately, quite important for the predictions of high energy emission. You can see that if you have it very low, then most of the emission comes out, or most of the non-thermal emission comes out at high energy gamma rays. But if it's higher, then actually you will have the spectra at daytimes at this dominated by synchrotron. Synchrotron is the second peak that appears in the X-ray domain after a certain time. So when magnetization is higher, this peak can become higher, and it correspondingly suppresses the very high energy emission. So low magnetization is more favorable for obviously for the high energy emission. Okay, a couple of light curves in different bands. The black one is well, these different panels are for these different magnetizations we're talking about. The black curves are volumetric optical light curves that we predict. And the red one is in the last band, and the blue is this so-called TV band, or the one that you can see by Cherenkov instruments. So one thing that we set out to prove, as I said, was that during the peak of the optical emission, you have more or less complete thermalization. That is, that this curve is close to the engine input curve. Basically, whatever you input by the central engine is transported into the optical domain and emitted there. This is no longer true at later times. We see that these two curves start to deviate from each other, and whatever is missing from here has to come out somewhere else. And first, it will come out according to this opacity picture that I showed earlier. It comes out from the thermal lab band, and actually, at the time, this thermal lab emission is sort of at its maximum. It more or less tracks the engine power at that time. So quite efficiently, this engine emission is processed into the GV gamma rays. Again, when you wait a little bit longer, we'll also start getting TV emission over the course of a couple of years. But unfortunately, the luminosity is quite a bit lower because the engine luminosity by that time has already had time to decline. And here, for comparison, are a couple of upper limits that were obtained for the LUT and for Veritas, which is a Cherenkov instrument. You can see that they are quite, in this case at least, they are quite far from what we predict, unfortunately. With CTA, you can get quite a bit better, but still in this case, you wouldn't even expect a detection with CTA, even with the most optimistic models. So this is sort of bad news for us. There is another event that we modeled, this the 2017 EGM. The good thing about this is that it was extremely close, comparatively speaking, of course. And in this case, actually, the lot limit already becomes almost constraining. So we're getting close. There was no detection, but it's almost at the point that we're close to what we predict. Unfortunately, the TV Veritas observation was still quite far away. But CTA, we could have, in the most optimistic scenario, could have hoped to see something. So yeah, there is hope, although it doesn't look too good. Okay, so a few words about future expectations. Here we're plotted basically the peak optical magnitude of a selection of superluminous supernovae along with the predicted gamma ray flux. Now, these gamma ray predictions are not, well, they are obtained by actually a simplified model, not this full source-consistent simulation. But they should be taken with a grain of salt, but they might give you a rough indication what to expect in the future. So according to this, there is, well, you should not bury all hope of detecting them at very high energies. Compare this, for example, this predicted CTA sensitivity curves to what's predicted. Okay, so in principle, since these events are, well, unfortunately they are rare, but since they are so bright, they can have cosmological implications, and actually people have tried to find a similar Phillips-like relation between the maximum luminosity and some other quantity like decline rate, which is would not be directly dependent on its redshift. If you can standardize them this way, and well, there are claims that you can, then well, you can use them the same way as 1A supernovae as standard candidates. You can write the standardized distance modulus, compare it what would be expected by your favorite cosmological model, where you get this mu as a function of redshift, and when comparing those, you can in principle constrain cosmological parameters, and they basically try to do this, of course, only with 20 events. So, but I mean, they say it's the first Hubble diagram with supernovae. Of course, the constraints that you get from this on the cosmological parameters are not yet competitive with other methods. You get a sort of an idea what to expect in the future. For example, when LSST is working, they simulated a sample of approximately 1,000 events and tried to estimate what kind of constraints you can put on cosmological parameters in this case. And for some reason, which I don't know much about this, but why this is, but they claim that the constraints on, for example, omega m are comparable to what we have now with other methods, but for some reason, the constraints on dark energy equation of state, they claim that they can get like 2 to 3 times better than we have now. Yeah, I don't have more comments on this because I don't know how exactly this works out. And here, well, here are the current rates compared to ordinary supernovae. There are several orders of magnitude rarer. At this point, we have only a couple of hundred of them. But with the advent of LSST, the most optimistic estimates are that we might get like 10,000 per year, which is already something. Okay, so this is a summary of this part. Basically, we found what we set out to do is that if you have this engine power of the model, and you compute this the radiative transfer self-consistently, you can validate some of the previous assumptions about this complete thermalization close to the peak, which is important because this is sort of whatever happens at the peak or close to the peak is used to or has been used in the literature to put constraints on this engine and the ejector parameters like the initial magnetization, initial spin period, ejector mass, and so on. Also, what we found is that in order to reproduce the late optical light curve with the magnetron model, you have to have a very efficient conversion of this magnetic energy that this magnetron outputs into particle energy, so that almost nothing is left in electromagnetic or magnetic form after this termination shock. Also, well, in comparative terms, again, we predict quite a bit of GV luminosity. Unfortunately, they are so far away that we saw that it's still not easy to detect them. And TV emission over the course of a couple of years. And, well, we are hopeful because the overall detection rate, which right now is at the level of a couple of hundred, is expected to increase rapidly in the near future. Also, it's worth noting that if we do detect either GeV or TeV emission from one of those sources, it basically is a smoking gun for this central engine model, because other modes don't. Well, you get gamma rays from radioactivity, but these are MEV gamma rays, so you wouldn't expect so high energy emission from other modes. Okay, so the future directions that we're trying to take our modeling, well, first and most obvious is to study as many of these events as we possibly can. Right now, the code that I've written is still serial and very slow. So the first step would be actually to try to parallelize it, which shouldn't be too difficult because it's a Monte Carlo simulations, and these are generally very amenable to parallelization. The next step is to apply this model to different kinds of explosion transients where this engine power is thought to be significant, the so-called despots and compact mergers and kilonovae. I'll say a few words about those in a moment. But to do this, well, we need to go to the drawing board a little bit. We need more careful computation of the interaction between this high energy radiation and in particular the ionization structure of the ejector, because these other kinds of transients typically throw out less mass than this classical supernovae, which means that they are more easily ionized, and this ionization physics becomes very relevant, for example, in the X-ray domain. Because if you have a highly ionized media, it's transparent to X-rays. If it's mostly neutral, it's completely opaque. So this is important to do. Also, if you have relatively small mass but a lot of power coming from the central engine, it can have a dynamical effect on the ejecta, which we right now also don't count. So one of the next steps is also to couple this magnetar wind to the outflow dynamics. Okay, so briefly about a few other kinds of transients where we expect this kind of engine power to be relevant. One is the so-called fast blue optical transients that I mentioned. They basically are also supernova-like events, but what sets them apart is that their light curves evolve very fast. Basically defined as events where the time about half maximum for the light curve is less than 12 days, which is significantly less than most either ordinary or even also supernova. Their hosts are more or less similar to the supernovae, at least for the luminous ones. But when you look at the diagram according to peak luminosity and rise time, you can see these black dots, these are these M-dots. They span a broad range of peak luminosity. So probably we are dealing with a quite a heterogeneous group, and also it's likely that the powering mechanism for all of those is not the same. But in some cases, as in the case of this 18 cow, so-called, the peak luminosities can actually rival the supernova. And this cow, also dubbed as in a moment. So about the power source, as I said, or did I don't know. Well, basically, radioactive decay is also disfavored for these events, simply because of this fast evolution of the light curve. There are several plausible alternatives, and we are mostly interested in this central engine one. But as I said, we're probably a heterogeneous group, so different events can be powered by different. The poster boy for this is the so-called aspherical cow. It simply comes from the fact that there happens to be a designation 2018 COW, and the large amount of data that's available for this, because it was so close and bright, enabled us to, yeah, I have a rather minor part of this, but they're able to constrain the outflow geometry, and want to see that it was highly aspherical. That's why it's an aspherical column. Basically, it was observed all the way from radio to optical, UV to the X-ray. So there's a lot of data available, and hence the rather stringent constraints. And this is one of the events that actually we would like to simulate with more, or model with more detailed simulations. But the problem right now is indeed that this part of this outflow is too tenuous. The ionization physics is relevant, which we don't have in the code right now. Okay, I will skip this and say finally a few words about another type of event that also may have something to do with this so-called engine power. Is the so-called kilonova, which are compact mergers of neutron stars. Well, when we talk about compact mergers and the associated gravitational waves, you have several channels that you can have. Probably have seen this picture before. We are interested in only one channel, is where we have inspiral double neutron star, and after the merger, the mass is not so high that it immediately collapses to a black hole, but at least for some time it remains a massive and spinning neutron star. This is the scenario that's most interesting to us. The poster boy for this kind of event is the GW 170817 gravitational wave event, for which we have a huge amount of data. First, the gravitational wave event, then you see the gamma ray burst, which comes from this jet that is launched right after the merger of this kind of black hole, or in this case, of the neutron star initially. Then you have the merger ejecta, so it gets thrown out, which powers the so-called kilonova, mostly optical, over a time scale of like a day. And finally, one is also radio observations, which are thought to be powered when this ejecta runs into the interstellar medium. So huge amount of information that you can get from this.
Sorry, can I ask, how do you know it's a boy? It's a poster boy.
I don't know.
Because of the ejecta.
Well, the James. Okay, and what does it have to do with the central engine? Well, so far, in this case at least, we don't have very strong indication. Well, there are some indication, but not very strong, that there might be some long-lived neutron star remnant there. But in principle, in general, regardless of this particular event, there is quite a bit of potential for this central engine idea, because if the neutron star is born, it spins fast because it's a strong magnetic field, and actually the energy budget that's associated with this spinning neutron star more or less maximally rotating, right? Because it's come together. It is enormous. So in principle, you can see from these theoretical light curves, its power can be quite big. It depends on the, of course, on the parameters, but its power close to the peak time can be a couple of magnitude higher than the classical R process radioactive decay, or basically radioactive decay of R process elements, correct? So it can surpass this by a couple of orders of magnitude. So it's worth looking into how this kind of thing would look like. Also, there is sort of another hint that in some cases you indeed might have a long-lived central engine there, which is for the reason that in many short gamma ray bursts, this was also a short gamma ray burst, and this is a different event. But in many cases, you see after the initial gamma ray burst peak, which is about a millisecond, you see extended emission, and this has to be powered somehow. So it's sort of an indirect hint that in some cases you might have a long-lived central engine there. Okay, so Also, you can ask the question, how much, if the neutron star does not immediately collapse to a black hole, how much extractable energy you have? This is sort of the total rotational energy. But if it's born very massive, you can have a situation that while it does not immediately collapse to a black hole because it's rapid rotation and also differential rotation, this differential rotation and the rotation itself is removed rather fast, and you might end up in a domain where it's unstable and collapses. So when you start going higher in the newborn neutron star masses, and initially your extractable energy goes higher and higher, but when they become unstable, then less and less energy that you can get from this neutron star before it flashes to a black hole. Okay, I think almost done. Okay, I will skip this and show a slide that basically is probably not much new to us. It's just to illustrate that this is kinds of events where you have both the gravitational wave event and the electromagnetic counterpart. You can have a lot of information from that, and then you do a lot of astrophysics, also cosmology, and so on. Basic idea is that if you have a gravitational wave signal alone, you will get only a luminosity distance directly, and also you don't know what the proper mass of these components was that came together. You only see the so-called redshifted mass. But if you have the electromagnetic counterpart, basically you can identify the redshift, and you can put this on the Hubble diagram. You have luminosity distance versus redshift. So a smoking gun for this kind of kilonova that we understand this process correctly would be if you see spectral lines from these R-process elements, because this kind of neutron star merger is predicted to create a lot of those elements that should power this kilonova. Okay, and finally, I think no, I cannot. I have to skip this due to stop time, so I'll stop here. Thank you.
Two questions, please, from the audience, and also online. You can just speak up or write to the chat with your question.
Probably I should have got it from the presentation, but do I understand correctly that these superluminous supernovae, they're in principle very similar to normal core collapse supernovae, just there's something a bit different?
They are associated with deaths of massive stars, but something is different there.
But do you know what?
No, well, somehow they are able to make this highly magnetized. Well, it's not clear. Actually, it is. It doesn't have to be a magnetite. It could be also this fallback. Somehow they activate this central engine. And also, you can ask the same question about, for example, gamma ray bursts. Also, this type, well, the so-called long gamma ray bursts. Also, they're associated with stellar deaths, but it's clear that not all supernovae are associated with something special.
Can I say that this star will end up as a normal supernova, this one as a superluminous?
I don't know. You probably need, well, one idea is that we need somehow to have the core to have a lot of angular momentum. How this works, maybe very low metallicity stars, for example, because if I recall correctly, they tend to lose less angular momentum over the lifetimes. Maybe some binary interaction. Yeah.
Then you should observe them in the early universe more, if it is
Well, how early?
Low metallicity.
Yes, well, for gamma ray bursts, I think the peak was redshift is about 2. For those, yeah, I'm not sure. Well, most of them are closer than 2, actually. Principally, you could see them further, but yeah, at this point.
Short remark before. Why no hydrogen?
It has lost its envelope before. Well, by either the final
Okay, you have some ejection.
Yeah, either ejected somehow, or there might be also a binary interaction that can.
But how is it? I mean, if it is a normal core collapse supernova, which is characterized by having hydrogen, do you have?
Well-
can you have? Do you also have like a normal type 2 supernova without the hydrogen? You don't, because that's how they classify.
Yeah,
or-
well, they are not type 2, they are 1B or 1C.
Yes, there are a great deal of core supernova.
Yes.
Don't have any hydrogen left, or almost no hydrogen left.
They are not called type 2 because it's by definition that they have,
Okay.
but it's one, well, 1A is different, but 1BC is core collapse, and they don't have.
Okay. I think.
Another question about detecting them. So what is actually needed? You need to have the light curve to pinpoint that this is superluminous supernova, or what do you need? Or you need the redshift.
Maybe you can tell me.
What is the limiting factor at the moment in detecting more of them?
Well, there are these surveys that scan basically a large or almost entire sky with a cadence of a few days. So in principle, it would be enough, except, well, it probably has to do with the limiting fluxes.
But you need
Yes,
just like, what do you need? You need the light curve in one filter, in one proton filter, or you need some?
Well, the more you have, the merrier. But I mean, our modeling was basically based on volumetric light curve. But I mean, of course, if you could have more details there and then spectral
But
line,
you
if you
also
want,
need-
you can.
You also need the redshift.
Sorry?
You also need the redshift, or you don't?
Yes, in principle, yes.
So for with these high magnetic fields, to what extent, say, if you observe it in radio and you take polarization observations of this region, say with using Faraday rotation, can you estimate this high magnetic field using that?
The engine itself is, I'm guessing it's hidden inside. Yeah, that's a good question. What is the time scale over which this ejecta becomes transparent to radio? I'm guessing it's quite long. Well, when people talk about radio emission, it's usually from the interaction of the ejecta with something outside. But in principle, well, yeah, I don't know. I don't know how much radio actually you expect because this our modeling also had this as the synchrotron, right? Which is usually associated with radio, but it peaks in X-ray.
Okay.
But if you wait sufficiently long, maybe I haven't thought about this in this.
Because you have already radio observations, so I was wondering whether you have polarization observations, like polarization readings of that observation as well, or not?
For the superluminous events, actually, we don't have. I don't think very well. Yeah, I actually haven't thought about it much because I'm sort of concentrating on the high energy, but I'm not sure that they actually have observations of this. For this F-port, yes. And actually, your question is relevant to this too, because the dominant model for this Worcester person is at this point is magnetic model.
Okay.
Yeah, but I don't have the answer at this point.
So, are there any exceptions where you get two peaks? Say, it spins down, but if something through accretion disk or some slightly massive body
There are
comes
this
in,
kind of undulations, yes.
and does it correspond to some spinning up of this central engine?
Well, the central engine generally does not spin. I mean, it spins up over the course of when it's born in milliseconds per second.
Okay.
After that, it most likely spins down. But as for several of peaks, in principle, you could have this There is all kinds of complicated things that can in principle be going on there. You can have the ejecta ionization state varies, becomes suddenly more transparent in some range, and in principle you could have it. But I'm not sure. There are undulations. I'm not sure it's sort of here. Top peak.
Okay. And like it's mostly spin down, but is there any way you can spin it up? Like again, or
equation.
what would be those?
But yeah, I don't know if you can make a plausible model where it's spins up. So in principle, how you can spin up a compact object by accreting stuff on it. But it has so strong magnetic field that it doesn't. It probably doesn't let it to be the so-called propeller regime where it's try to feed this material it's going from.
Can stop later, but much later.
Because I mean, by the same token, that it creates this cavity. It's electromagnetic pressure that creates this cavity in the first place, so it doesn't let stuff go in.
Okay. I was thinking of supermassive black holes where you actually get, say, 2-3 times if you just observe the jets, where you can get more than 1 or 2 cycles of these ejections.
Yeah, but I mean, in this case, you can sort of. It has to do with the feed, how you feed it, right?
Yeah.
You can have several episodes of this feed.
Okay.
In this case, probably not.
Okay.
You mentioned that the superluminous supernovae were discovered about 20 years ago, but have any of the earlier supernovae reclassified as superluminous?
Good question. I don't know.
They are too far away.
Yeah, but I mean, if you talk about.
I mean, nowadays,
But if you didn't have a redshift then, well, if you don't have a redshift in principle, what I know is that the late time, but not so late, not very late, but late time light curves are actually comparable to 1C normal supernovae, those that have lost its hydrogen and helium. Well, like the supernovas there. But I don't know if it's been attempted. So, but what's your idea? Suppose we classify some of them like this.
I know a big collection of photographic plates.
I
was curious if it was possible to find them there.
Yeah. I don't know. I mean, based on this metrical Broadband light curves, whether you probably cannot tell them immediately apart.
I have another short, maybe stupid question about late stages of star evolution. You mentioned Chandrasekhar mass of the core. Usually you talk about Chandrasekhar mass regarding white dwarfs. Is it the same value or would it be different? Because the composition is different.
I'm not sure about the exact value. I think it's comparable. Well, basically, it's that the core is supported by electron degeneracy pressure. And at some point, I don't know how, well, it probably depends somewhat on the composition, but quantitatively, I can't tell you. I'm guessing it's similar. So at some point, you will have, it can't support. Basically, it's, it should be similar.
Questions? Nothing in chat.
Maria.
Thanks.
Do you see something in?
I do. Hi.
Hello. First of all, sorry, because I'm a bit lost between time zones. So I arrived 10 minutes before you finished the talk. So I think I will need to see the talk again, the recording. So, but I did not fully follow the science. So, but I saw that you wrote that in one of your slides that is missing from the numerics, it's missing the parallelization of the code you would like to do in this supernova model that you have.
Yes.
So I was wondering, so I hear that a GPU it's really suitable for parallelization and it's really fast. And I want to know if you were thinking on doing GPU parallelization or if you would be interested on knowing more about how to do GPU parallelization.
Yeah, I have to say I don't know. I haven't thought about this in this context. I would be interested to know what are the benefits by doing it on GPU as opposed to CPU. If you can tell me that. Well,
No, I cannot tell you that, but maybe we can have one seminar with Josep Pata from Cabify and he can tell us about GPU programming. We can make one of these astronomy seminars and yeah, because maybe much of us can benefit from that. So I don't know, I have here a lot of fuss with GPU nowadays. So myself, I want to know more and I want to know if there is someone interested also in observatory to know more about it. I know Ryan is interested, so yeah, but maybe I can talk privately with Johan and see if we can make this one of these Astronoomia seminars with Josep Pata, or maybe even Sven.
Did you say something specific about this GPU parallelization of Monte Carlo codes?
No, but we are using right now, Sven in Cabify is using GPUs in MCMC. With MCMC, so but apparently it's extremely fast. It's I don't know, it blows your mind.
There might be one problem with this that this in my setup if you increase the number of particles, which you would ideally want to do, and run it in parallel, you need a lot of memory. So can this be a problem with GPUs?
But in any case, okay, let's discuss once I'm back. And maybe we can discuss before with Joseph what is your specific problem and maybe he can discuss about it when he comes or okay. But in any case, thank you. Greetings from Tenerife and enjoy the day.